Module 32, Lecture A, Persistence Deployment. By the end of this lecture, you will be able to choose appropriate persistence formats for Scikit-Learn models and pipelines, save and load fitted artifacts while considering security and environment compatibility, and validate persisted or exported models after deployment style loading. Persistence formats. Choosing persistence formats. When saving a fitted Scikit-Learn model or pipeline for reuse, choose a storage approach based on reliability, portability, security, and how the model will be used. Production systems often need models to load quickly, run in different environments, or be reproduced later, so the format matters. Treat the field pipeline as one artifact, so pre-processing steps and model settings stay consistent and avoid errors. In Scikit-Learn workflows, pickle and joblib are common ways to save models within Python. Pickle is convenient for experiments, while joblib is better for large numerical arrays and complex models. Because both depend on the Python ecosystem, they work best when you control the deployment environment. If a model must run across different platforms or languages, use an interoperable format that supports both the model and its pre-processing steps. Choose a model persistence format based on how and where the model will be deployed. Joblib works well for regular retraining in Python, while pickle can be acceptable for small local experiments if used carefully. For sharing across teams or platforms, use an interoperable format that can capture the full pipeline and plan for package versions, metadata, and access control as part of deployment. Pickle persistence. Pickle provides a simple way to save a trained Scikit-Learn model or pipeline by storing the full Python object, including its structure and learned parameters. This lets you reload the model later without retraining, as long as you use a similar Python environment. It is especially useful for moving a complete workflow, such as pre-processing plus a classifier, from experimentation into later scoring, while keeping data processing consistent. Pickle works well with Python objects, so it can save Scikit-Learn pipelines that include both standard and custom components, as long as those components are available when the model is loaded. This makes it useful when training and inference use the same codebase. However, because Pickle depends on Python classes and package versions, changes to the code or environment can break loading, so the save and load environments should stay consistent. Pickle is useful for saving Scikit-Learn models when you will reload them in a trusted Python environment with the same dependencies. It is not a universal format for sharing models across systems or languages. In deployment, track the Python and library versions used during training, and treat pickle files carefully because they can pose security risks. Python code, pickle persistence. This example shows how to save a fitted pipeline using pickle, which preserves the structure of Python objects. After reloading the pipeline, matching predictions confirm that it can be used reliably in a deployment-style workflow. We set up the tools for a simple machine learning classification task by importing NumPy for numerical work and Scikit-Learn for modeling. From Scikit-Learn, we load the breast cancer dataset and use logistic regression to perform binary classification. We import key Scikit-Learn tools to build and evaluate a machine learning workflow. The accuracy score measures how well predictions match the true values, while the train test split function separates data for training and testing on unseen examples. The make pipeline utility connects processing steps into one workflow, and the StandardScaler prepares features by centering and scaling them for better model performance. The code imports joblib, a library for efficiently saving and loading Python objects. It is commonly used to store trained machine learning models and pipelines, so they can be reloaded later for predictions or analysis. This helps keep model use consistent and reliable in production. This script shows how to save and reload a trained machine learning pipeline using joblib. It builds a pipeline with scaling and logistic regression, trains it on the breast cancer dataset, and saves the fitted pipeline so its full structure and learned state are preserved. After reloading, the same pipeline can make consistent predictions without retraining, which is important for reusing models in production. Joblib persistence. Joblib is commonly used to save Scikit-Learn models and pipelines because it handles Python objects with large NumPy arrays efficiently. This makes it well-suited for storing model parameters and complete workflows, including preprocessing and classification. By saving the full pipeline, joblib helps ensure the same transformations are used during training and deployment. Joblib is useful for efficiently storing and loading large numerical arrays in Python, especially when working with tools like Scikit-Learn and NumPy. It can compress data to reduce file size, though this may trade off some loading speed. Its main limitation is portability, since it preserves Python-specific structures and is not well suited for non-Python applications. Joblib files should be treated as trusted artifacts because loading them can run actions stored inside serialized Python objects. This makes joblib appropriate for controlled internal workflows, but unsafe for unverified external files. It also does not guarantee long-term compatibility across library versions or systems, so teams often store training environment and dependency metadata. Within a Python ecosystem, joblib remains a practical choice for Scikit-Learn models, especially when large numerical arrays are involved. Python code, joblib persistence. Save the trained pipeline with joblib, then reload it as you would in a deployment service. After loading, compare its predictions with the original pipeline to confirm they match. The code uses the I/O module to create an in-memory data buffer. This buffer can hold the serialized pipeline, allowing it to be saved and loaded without writing to disk. This is useful for quick testing and deployment. This setup imports the main tools needed to build and evaluate a simple machine learning model. It includes libraries for saving objects, numerical work, and machine learning, along with the iris dataset for classification. It also brings in logistic regression, accuracy scoring, data splitting, a pipeline tool, and feature scaling, so the model can be trained and tested in a clean, consistent workflow. We load the built-in iris dataset from Scikit-Learn, a simple dataset often used for demonstrations. Its input measurements are separated from the output labels, giving us the data needed to train and evaluate a machine learning model. The code verifies that the feature data and target labels have the same number of entries. This ensures each training example has a matching label, which is required for supervised learning. If they do not match, it raises an error to prevent training on misaligned data. The dataset is split into training and testing sets using Scikit-Learn's train test split function. 25% of the data is kept for testing, while a fixed random state makes the split reproducible. Stratification preserves the class balance in both sets, which helps when classes are imbalanced. This lets us evaluate the model on unseen data for a more realistic measure of performance. We build a pipeline that combines feature scaling with logistic regression. The scaler normalizes the training features, and the model then learns from the scaled data and labels. This keeps pre-processing and model fitting together in one reproducible, streamlined workflow. An in-memory buffer is used to temporarily hold the fitted pipeline as if it were a file. Joblib saves the pipeline into this buffer, converting it into bytes that can be stored and later restored. Loading those bytes with joblib reconstructs the pipeline, confirming that it can be saved and reloaded without losing functionality. to verify that saving and reloading worked correctly. We compare predictions from the original pipeline and the reloaded pipeline on the same test data. If the two prediction sets match exactly, it confirms that the model's behavior was preserved during serialization and deserialization. The loaded pipeline is evaluated by comparing its predictions with the test labels to measure accuracy on unseen data. The process also reports the Scikit-Learn version, the saved model's file size, and the accuracy rounded to 3 decimal places. Finally, it checks that the original and reloaded pipelines make the same predictions, confirming that saving and loading preserved the model's behavior. This script shows how to save and reload a machine learning pipeline with joblib. It trains the pipeline on the iris dataset using scaling and logistic regression, serializes the fitted pipeline, then reloads it and compares predictions on the test data. The matching predictions confirm that serialization preserved the model correctly, and the output reports the Scikit-Learn version, artifact size, loaded pipeline accuracy, and whether the predictions match. Safe model artifacts. Cloudpickle serialization. Cloudpickle is useful for saving Scikit-Learn models that include custom preprocessing, transformers, or notebook-defined functions. It preserves both the model parameters and the logic used to prepare input data, so the full pipeline can be reused later for scoring or testing. Cloudpickle artifacts should be treated like executable code, because loading them can run Python code. Only load serialized models from trusted sources, such as controlled pipelines or verified registries, and avoid unknown files from untrusted locations. Organizations should use clear ownership and access controls, so shared models are traceable, approved, and handled securely. Cloudpickle artifacts depend closely on the environment where they were created, including Python and library versions such as Scikit-Learn, NumPy, and Pandas. Small version differences can change behavior, even if the artifact loads successfully. To reduce risk, save the exact environment details, reproduce them during deployment, and test the loaded artifact with known inputs and outputs before using it in production. Python code. Cloudpickle serialization. This section shows how to persist a fitted Scikit-Learn pipeline using Cloudpickle-style serialization without saving local files. It also checks that predictions from the loaded pipeline match the original predictions, confirming that the model was restored correctly. The setup imports the main tools needed for a simple machine learning workflow. NumPy for numerical work, Scikit-Learn for building and evaluating models, and Cloudpickle for saving and loading Python objects. It also loads the iris dataset as the classification data source and selects logistic regression as the model to train. We import key Scikit-Learn tools for building and evaluating a machine learning workflow. The train-test-split function separates data into training and testing sets, while the pipeline class keeps preprocessing and modeling steps consistent. Function transformer supports custom transformations inside the pipeline, and StandardScaler standardizes features by centering them and scaling them to unit variants. We import the accuracy score function from Scikit-Learn to evaluate model performance. It compares the model's predictions with the true test labels and reports the proportion that were predicted correctly. We load the classic iris classification dataset from Scikit-Learn to use in a machine learning example. Its feature data and target labels are separated, so the model can be trained and evaluated later. Before training, confirm that the feature data and target labels have the same number of rows. This ensures every example has a matching label. If they do not match, raise an error to stop processing invalid data. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, and a fixed random state makes the split reproducible. Stratifying by the target variable preserves the class balance in both sets, helping the model train and evaluate on representative data. The add petal ratio function expands a feature array by adding one new column. It calculates petal length divided by petal width using the third and fourth columns, then appends that ratio to the original data. The result is a modified feature set that includes this additional petal ratio information. This pipeline combines feature engineering, scaling, and classification in one consistent workflow. It first adds a petal ratio feature by comparing petal length to petal width, then standardizes the data so features have comparable scale. Finally, it applies a logistic regression model with a fixed random state and a set iteration limit, making the process ready for training and reliable prediction. First, the pipeline is trained on the training features and labels so it can learn patterns for prediction. It is then used to predict labels for the test data. These initial predictions are saved, so they can later be compared with predictions from the serialized and reloaded pipeline to confirm they match. Cloudpickle can serialize a machine learning pipeline into a byte stream, capturing both its structure and learned parameters. That byte stream can then be deserialized to recreate the original pipeline, so it can be used again as before. This shows how complex Python objects can be saved and restored without writing them to a file. After loading the saved pipeline, we use it to predict on the test data to confirm it still works correctly. We then compare these predictions with the ones made before saving. If they match exactly, it shows that serialization and deserialization did not change the model's behavior. After loading the serialized pipeline, we check that it still behaves like the original model. We compare its predictions with the original predictions, calculate its test accuracy, and report that accuracy rounded to 3 decimal places. We also print the Scikit-Learn version and the serialized pipeline size to support reproducibility, compatibility checks, and storage awareness. This script shows how to save and reload a Scikit-Learn machine learning pipeline using cloudpickle. It trains a pipeline on the iris dataset with a custom feature, scaling, and logistic regression, then serializes the trained pipeline into bytes and loads it back. By confirming that the reloaded pipeline gives the same predictions and reporting its accuracy, the script demonstrates a reliable way to preserve a model without using local file storage. Trusted Skops loading. Trusted Skops loading helps restore Scikit-Learn models more safely by checking saved models before they are used in production. Unlike standard Python serialization, which may run embedded instructions, Skops loads only objects that are expected and trusted. This matters because models can include preprocessing steps, estimators, and custom transformers. So sensitive settings like hospitals or banks need assurance that no unintended or tampered components are included. Trusted Skops loading makes model restoration a deliberate approval step rather than an automatic action. Before loading, it identifies the object types in the model, including standard estimators and custom classes, so teams can decide whether they are safe for the target environment. Familiar components may be approved quickly, while unexpected custom transformers should be reviewed, especially when models move from development to operations. Trusted loading helps ensure a saved model will run correctly in production, not just securely. Teams should check the artifact's dependencies, such as library versions, against the deployment environment to reduce runtime errors and inconsistent predictions. Loading the model first in a controlled staging area and recording trusted types makes model persistence a more reliable and disciplined process. Artifact trust. Artifact trust means treating a saved model or pipeline as a production asset that may contain executable code, class references, and environment assumptions. Loading an artifact from an unknown source can create security risks or reliability problems, especially in production. Trust depends on knowing where the artifact came from, how it was created, and whether it has been approved for your environment. To trust model artifacts, use both technical safeguards and disciplined processes. Store them in secure internal registries or repositories with access controls and audit trails, and include metadata about the model, training pipeline, input schema, package versions, and training environment. Because changes in tools or preprocessing can affect behavior, always verify an artifact's requirements and lineage before treating it as trusted. Artifact trust in deployment means validating a model both before and after it is loaded. Before loading, confirm its source, integrity, storage controls, dependencies, and that it has not been changed. After loading, test that it accepts the expected inputs and performs consistently with training results. This is especially important for models used in high-impact decisions where mistakes can cause real harm. Deployment validation. ONNX export. ONNX export lets a trained model move from development into deployment environments that may use different languages or libraries. It turns the model into a portable computation graph, so a Python-trained model can run in systems where the full Python stack is not practical. Because this is a change in representation, not just a file conversion, the exported model must be validated to ensure it behaves like the original and keeps its expected performance. Validate an ONNX exported model by comparing its predictions with the original model on realistic inputs, including typical, edge, and deployment-specific cases. Make sure any preprocessing, such as scaling or encoding, is either exported correctly or reproduced in the deployment system. Small precision differences may be acceptable, but only if they do not affect the intended outcome, especially in high-risk uses like medical applications. The goal is to confirm that the ONNX model remains consistent, interpretable, and safe to use. When validating an ONNX export, focus on whether the deployment setup handles inputs and outputs exactly as expected. Check the input schema, data types, feature order, and output meaning, because small mismatches can make predictions look valid while being wrong. Validation should use the same runtime and interface as production, with test cases that have known results. Documenting model versions and settings also helps keep future updates consistent and reliable. Environment reproduction. To validate a saved model reliably, you need to reproduce the software environment it was created in. A Scikit-Learn pipeline can depend on specific versions of Python, Scikit-Learn, and related libraries, so version changes may subtly affect its behavior or predictions. Recreating both the model and its original conditions helps ensure validation reflects how the model will perform in production. To reproduce a model reliably, treat the runtime environment as part of the model package. Document key details such as the operating system, Python and library versions, hardware assumptions, and required external resources. In production, isolated environments or containers help keep deployment consistent. This prevents errors caused by mismatched preprocessing, settings, or dependencies, and makes it easier to separate true model problems from operational issues. After deployment, validate a model by comparing its behavior in the new environment with the original training setup. Test it with varied inputs, including edge cases such as missing data or unusual profiles, to detect output differences. If results differ, determine whether the cause is expected variation, a system change, or an unintended environment shift, so the model remains reliable and trustworthy. Python code, environment reproduction. Validate a loaded model by recreating the original conditions and comparing its predictions before and after saving. Check that the software versions are consistent and that the outputs match closely. The script imports the input and output module to work with data streams. Here, it creates an in-memory byte stream, so the model can be saved and loaded without using disk storage. This makes testing model persistence faster and more controlled. This setup imports the main tools needed to build and evaluate a simple breast cancer classification model. It uses joblib for saving and loading objects, NumPy for numerical work, and Scikit-Learn for the dataset, logistic regression model, train test split, accuracy evaluation, and pipeline creation. A StandardScaler is included, so features are normalized before training, helping the model handle differences in feature scale. We load Scikit-Learn's breast cancer dataset, a built-in dataset for classification. The feature data and target labels are separated, so the dataset is ready for modeling and evaluation. Before modeling begins, the code verifies that the feature data and target labels have the same number of rows. This confirms that every data point has a matching label. If they do not match, it raises an error to warn the user about inconsistent dataset dimensions. We split the dataset into training and testing sets using Scikit-Learn's train test split function. 25% of the data is kept for testing, while stratification preserves the original class balance. A fixed random state of 42 makes the split reproducible across runs. We build a machine learning pipeline that first standardizes the input features, then trains a logistic regression model. Scaling gives the features a mean of 0 and a standard deviation of 1, which helps logistic regression work reliably. The model is configured for reproducible training, and fitting the pipeline applies the scaling and learns from the training data in one process. An in-memory buffer can temporarily hold a trained model, while joblib saves it as a byte stream. The byte data can then be extracted for storage or transfer, and joblib can load it back to recreate the model in memory. This confirms the model can be saved and restored without losing its functionality or accuracy. To verify that saving and reloading a model preserves its behavior, compare its predictions before and after loading on the same test data. The match rate is the proportion of predictions that are identical between the two versions. A high match rate confirms that the persistence process kept the model consistent. The code compares the original model with the model loaded from the saved artifact by generating predicted probabilities on the same test data. It focuses on the positive class probabilities from each model, then finds the largest difference between them. This checks whether the loaded model reproduces the original model's outputs consistently. This check verifies that a saved and reloaded Scikit-Learn model behaves the same as the original. It reports the Scikit-Learn version, the loaded model's test accuracy, the prediction match rate between the original and loaded models, and the largest difference in their predicted probabilities. The reproduction check passes only when every test prediction matches, confirming consistent results after loading the model. This script checks whether a trained machine learning model behaves the same after being saved and loaded again. It trains a scaled logistic regression model on the breast cancer dataset, saves it with joblib, reloads it, and compares the original and restored model on the test data. It reports the Scikit-Learn version, accuracy, prediction match rate, and the largest difference in predicted probabilities. If the predictions match exactly, the persistence and environment reproduction check passes. Post-deployment checks. Post-deployment checks confirm that a model works reliably after it is loaded in a production-like setting. Run known validation inputs and compare the results with pre-deployment outputs to ensure labels or predicted values remain consistent. This helps catch changes caused by serialization or preprocessing, which is especially important in critical uses such as loan approvals or fraud detection. After deployment, check the full prediction pipeline, not just the model. In Scikit-Learn workflows, preprocessing, such as scaling and encoding, must match what was used during training, or predictions can fail. Use realistic data and edge cases to confirm that the model, application logic, and data handling all work consistently together. Post-deployment checks confirm that a model is not only accurate, but also ready to run reliably in production. They verify that the model responds quickly, uses resources efficiently, handles errors clearly, and can manage real traffic. Monitoring should detect unusual behavior, and metadata such as model version and training date should be available for troubleshooting. Together, these checks support a disciplined release process that connects model validation with operational oversight. Python code. Post-deployment checks. After deployment, validate the loaded model to ensure it still behaves as expected. Compare its predictions with trusted reference outputs, and confirm that preprocessing steps and probability results remain consistent. We import NumPy for numerical work and Scikit-Learn for machine learning tools. We also load the iris dataset using Scikit-Learn's dataset loader, giving us flower measurements and species labels. These imports provide the basic tools and data needed for later model validation and deployment checks. We import key Scikit-Learn tools to build and evaluate a logistic regression classifier. The dataset is split into training and validation sets. Accuracy is used to compare predictions with true labels, and a pipeline helps combine pre-processing with the model in one streamlined workflow. StandardScaler from Scikit-Learn is used to standardize features by subtracting the mean and scaling them to unit variance. This helps features with different units or ranges contribute more evenly in a machine learning model. We load the built-in iris classification dataset from Scikit-Learn for demonstration and testing. Its feature data and target labels are separated, so the dataset is ready for later processing and modeling. Before modeling begins, the code checks that the feature data and target labels have the same number of rows. This confirms that every feature set has a matching label for training. If they do not match, the code raises an error to show the data is not properly aligned. The dataset is split into training and validation sets, so the model can be evaluated on data it did not see during fitting. Using Scikit-Learn's train test split, 25% of the data is reserved for validation, while stratifying by the target keeps class proportions consistent across both sets. A fixed random state makes the split reproducible, producing separate features and labels for training and validation. A machine learning pipeline is built by combining feature scaling with logistic regression. The scaler standardizes the input features so the model can train more effectively, and the logistic regression model is configured for reproducible results. The full pipeline is then fitted to the training data, so it can learn patterns and make predictions on new data. Before deployment, the model is run on the validation data to create trusted reference outputs. Its prediction method provides benchmark class labels, while its probability prediction method provides the likelihood of each class. These saved labels and probabilities form a baseline for checking the model's behavior after deployment. To simulate deployment, we reuse the previously trained model as the loaded deployment artifact, rather than loading a new one. We then apply it to the validation data to generate predicted labels and class probabilities. This checks that the model produces consistent results before and after deployment. To confirm the deployed model behaves like the reference model, compare their predicted labels for an exact match, and check that their predicted probabilities are nearly the same within a tiny tolerance. Together, these checks verify that both the final predictions and the model's confidence remain stable after deployment. We evaluate the deployed model by comparing its predicted labels with the true validation labels to measure accuracy. We also compare its predicted probabilities with those from the reference model, checking the largest difference to confirm the model's behavior remains consistent after deployment. The output summarizes checks used to verify a loaded Scikit-Learn model. It reports the library version, validation set size, and model accuracy, then confirms whether the loaded model's predicted labels and class probabilities match the reference results. It also shows the largest probability difference to reveal any meaningful numerical discrepancy. This script checks that a deployed machine learning model behaves the same as it did before deployment. It trains a scaled logistic regression model on the iris dataset, saves its validation predictions and class probabilities as reference outputs, then compares them with outputs from the loaded model. The check confirms that predicted labels match exactly, and probabilities stay within a very small tolerance. It also reports the loaded model's accuracy and the largest probability difference, helping verify consistent deployment behavior. In this lecture, you learned to choose appropriate persistence formats for Scikit-Learn models and pipelines, save and load fitted artifacts while considering security and environment compatibility, and validate persisted or exported models after deployment-style loading. Congratulations on completing this course.
Thank you for your attention. See you all in the next lecture.